My name is Bernie Wu. I'm the VP of Strategic Partnerships and Business Development for MemVerge. And I'm a fairly simple guy. I take my coffee black, but I take a lot of it.
Welcome back to the MLOps.community podcast. I am your host, Dimitrios. And, normally I like to take my vitamins. And I generally take quite a few vitamins. I do, an array of vitamins, vitamin D, vitamin B, vitamin C, vitamin A, all that good stuff. I also have been known to take some mushrooms, not the hallucinogenic kind, the kind that help your brain function. And oh my, I wish I would have remembered to take them today because I did not. And this conversation, I was hanging on by a thread. Bernie brought some serious learnings to me. He helped me see things in a different way, specifically around memory allocation, elasticity of memory. And it just so happens, funny enough, ironically, that I should have taken these pills to help with my own memory, not the hardware memory, my own. If anything Bernie says piques your interest, feel free to reach out to him. He is very cool and very open to chatting with new people. Here we go. One thing that most of the time we'll snark at when people say this is the word or this expression of, you just have to think about it by first principles. You have to apply first principles thinking to it. And I know it is great, but it's almost been overused since it came into fashion and Elon Musk started using it. And now when you hear people saying it, I don't really trust that they actually, A, even know what that means, and B, actually do it. But in the pre-conversation that we were just having, the only thing that I could think about is your vision right now that I want to get into with not looking at GPU shortage in the market being the problem, looking at memory shortage in the market being the problem. That is what I would consider taking things to first principles.
Yeah, I know. I agree. It's funny you mentioned first principles because a long time ago I went to UC Berkeley, and the emphasis, even at the undergraduate level, is getting everything down to first principles. If you don't understand the first principles, you're not going to graduate from this place. But I do think that in this industry, I'll start out with this little factoid. The bulk of the industry is going to be delivering on production. That's where you get an ROI on all this AI investment that's going on in the industry, and the transformer model is kind of taking over the world. Well, the transformer model and foundation models and things like that, they I believe the number is around 0.1 flop per byte. Or in other words, there's 10 bytes of memory movement or loading into registers for every floating point operation on average. And so it's a very data intensive area. And on the flip side, in the news, there is all the stories about GPU shortages and things like that. But if you actually look at how people size their purchases of GPUs, it's based on, here, my model's this big, and therefore I need this much memory, and each GPU has this much HBM per GPUs, therefore I buy X number of GPUs. That's how it was done. And you find out that a lot of times the GPUs are then purchased that way, and often they're underutilized because they're memory bound. And so some of these models that were trained, I know at least at scale, their utilization was down in the 30% level. So if you could actually get more utilization, obviously you wouldn't need so many GPUs. But they are memory bound. So we are working to solve that. It's a complex problem. It's going to take some new memory technologies, new software, which is what my company's working on, and it's going to percolate all the way up through the stack. I start seeing signs of that already. There are new kinds of schedulers are going to have to be developed and things like that to handle a more composable memory architecture. Yeah.
Well, yeah, talk to me about how you see memory. Right now, it almost feels like we are memory scarce. How would a memory abundant world look?
Yeah, in a memory abundant world, well, I would say that you would have very common in things like Kubernetes and AI environments. You have these things where you run out of memory and then you start spilling to disk, and when you start spilling to disk, all of a sudden your performance grinds to it runs 400 or 500% slower, that kind of thing. It starts swapping and things like that. Or in some cases, because you don't even have the option to swap to disk, these things just get killed. They're killed or whatever. But so as an example, in that kind of use case, we're working on a situation where we have this elastic memory. We have this surge capacity of memory in a separate pool, and then when we detect that something is running out of memory, a particular compute instance, we just give it a shot of memory, and until the problem goes away, then we reclaim it and assign it somewhere else. So I think part of the overall solution, kind of like what people are doing with GPUs, is to pull things together, and you can get higher efficiency, and then also you can address fluctuations in demand as workloads go through different compute instances, and add either more GPUs or add more memory. There's a more, in other words, the infrastructure needs to get more elastic and composable.
Well, it's interesting that you talk about how a lot of times you're seeing 30% utilization rate, right? But then there are those spikes that will kill the job. And so you're trying to help for that spillover when you get that spike,
right,
so that you don't lose everything.
Right. Yeah, so that's another interesting area. There's a lot of, actually, because the AI ML area is a relatively new industry, and because you need to preserve these models, they take a long time to run. There's been a lot of work done at the framework level, the software, the PyTorch level, et cetera, to take checkpoints of things and save those states so that between training epochs, something crashes, you can at least restore, or if you overshoot the model training, you can roll back, et cetera. But those are interesting technologies, but they I don't think they can address all the different use cases for example, when a system just overheats or memory failures occur, and especially at scale. I think I was at a conference, and they said that some of these larger models that get up to, they're planning to build models with 1 million GPUs, and at that kind of scale, you're going to have 30, 40, 50 GPU failures per hour. So a lot more resilience has to be built into the architectures. And if you know anything about memory, as soon as the power or something goes off, you lose it. So we're also working on what we call checkpointing technology at the memory level. So the ability to save machine state and memory state at that level, as well as the framework level. And I think between the combination of those two, we'll get much higher resilience and be able to run all these long-running training jobs or long-running inferencing jobs. Now they're actually going to become inferencing services, so they need to be much more resilient than they are right now.
What do you mean by inferencing services?
Well, I think, as things go into production, we go from what fundamentally from a scheduling operation standpoint is more of a batch operation, batch to train this, batch to train that, to a service where we're constantly, dealing with maybe hundreds of thousands of consumers, and this thing has to run like any other web service, So its resilience, its ability to be migrated to new infrastructure as old infrastructure needs to be upgraded, all those kinds of tools that, I'm sure the MLOps community is very, very familiar with. They're going to be needed, and so we're interested in collaborating with your community to help bring those tools, the right tools, to handle this new onslaught of demand for memory. Yeah.
Well, it's funny you mentioned how it's fairly common for GPUs to go offline. I think the best way I've heard it was when we had our AI quality conference. Todd Underwood, who was head of the research platform at OpenAI, He said, you can just look at a GPU the wrong way and it'll go offline. And so he was just obviously taking it to the extreme and making jokes about how sensitive GPUs are and how finicky they are and how difficult it is for people to actually get that. And then in that same talk, he talked about how the other part that is complicated to really get right is knowing when to checkpoint. Because he's like, yeah, maybe you say, okay, I'm going to checkpoint every second. But what happens if it doesn't go offline, or on average, GPUs go offline every 100 seconds? Then you should be okay to do it every 50 seconds or every 25 seconds, right? But what happens if it goes offline every 3 seconds? Then you really have to be figuring those things out and then doing the calculations and recognizing it. And another person that we had come on here from Nebius Cloud was talking about how these checkpoints are just so big when he's training these models. So you can't be that sparing with how often you're checkpointing because it adds up quickly. I think if I remember correctly, it was like 3 terabyte checkpoints every time.
Some of the training models are getting up to that size, and writing that all to a file system, even a high performance file system, is becoming a bottleneck. And then also restoring it. So so one area where some of this memory technology that I'm working on is relevant is to create a memory pool that can act as a cache to basically dump all that stuff very quickly into memory, which is much faster. Obviously, it's about memory speeds are about the latency and all that kind of stuff. But it can be up to 10x difference by dumping it into memory and then asynchronously bleeding it off into the file system. That way you minimize the interruption period of the checkpoint. Because that is a problem. The checkpoint overhead is not surprising in a lot of training models to be 25-30% of the total training life cycle is spent on just doing the checkpoints.
Checkpoint management.
Right.
So basically you're saying, hey, what if we just had a Redis type of thing where you dump it into memory, it's cached, and then slowly it gets offloaded from that memory.
Right.
So you don't have to be sitting there taking the time to offload the checkpoint and then come back online.
Some of that's been applied in other industries like the high performance computing industry. They've had these giant clusters for decades, and they're running a model that runs for a whole month, simulation of a nuclear explosion or whatever they're doing. And they use this kind of checkpointing approach. So I think some of those techniques will have to come into play here. And then there's other needs for memory caches. So for example, on the inferencing side, what's happening is that in order to scale it, the models are getting so big. Like the latest Llama 405 a 405 billion parameter model now it doesn't fit in most GPU nodes, and now needs to be distributed. And so now people are not only figuring out they've already figured out kind of how to distribute training with 3D parallelism and all this kind of stuff. And now they're trying to figure out how to distribute inferencing. And one of the first things that people realize that, hey, this is a 2-stage process. So there's there's kind of a pre-prompt phase, which is CPU intensive. And then there's this decode phase, which is really purely, memory bound. And so they're starting to split the architecture. But the prompts are also getting so long that the KV weights in these training models that goes up quadratically with the length of the prompt. And so those things don't fit in memory. So now they have to start distributing the memory. So we have a distributed GPU and a distributed memory problem. And anytime you deal with memory, the first thing that happens is it gets fragmented, And so how do you manage all that stuff? So I don't think there'll be any shortage of work for companies like ours and the rest of the memory industry in trying to solve some of these problems. And they're really cool problems because, like I said, in this revolution, if I compared it to the big data revolution, there's a lot of things that the infrastructure area can do to innovate and improve this overall stack.
Yeah, it's really attacking that hardware side of things, which, the big data revolution, I think you mentioned before how it it was a revolution, but not as hard on the whole stack.
Yeah, same processors, actually just using lower grade servers. You didn't need to have your high end server. The whole trick was scale out, not up. Here, I think I would contrast that because these workloads are going to get more. Right now, most of this memory problem is what I would characterize as capacity bound and then secondarily bandwidth bound. But I think latency bound, which is the other concept in when you talk about what do you mean by memory bound? It's either capacity, latency, or bandwidth, or both, all of them. I think the latency bound issues are going to become more and more critical because the pipelines are getting more and more complicated, and so the end-to-end time is becoming a factor. If you're sitting at your computer, you type something in and you get an answer back in 200 milliseconds, life is good, right? Now these computers are going to go off and start reasoning and do do some sort of, multi-agentic kind of RAG LLM pipeline. And so there's a big difference between waiting 10 seconds for the answer and maybe waiting for, 10 minutes, right? And so getting faster devices, which is memory, basically, that's where memory really tops, using conventional, flash storage, using more memory more aggressively to help compress those pipelines, increase the utilization and throughput. It's going to be key. Yeah.
Well, talk to me about this distributed memory problem. And when you go into that type of a problem, can you break down how you think about solving it?
I think it's going to be sort of at the lowest level, things like models like the VLLM model was first to pioneer it, but they built a virtual memory operating system inside basically inside the HBM memory space, so they could page and have uniform sized blocks and manage memory that way, because every prompt that comes in creates a different size KV set of weights, right? So you're constantly fluctuating it, so you had to have some order to that allocation of that memory. Now these things don't even fit. So now you have this same a problem of allocating memory, but now it spans multiple nodes, multiple GPUs, and even multiple nodes. So it's going to take some kind of scheme, kind of a scheduling scheme, which is something else that we're starting to work on at our company, is how do we schedule these resources? And it's not just scheduling GPU resources, but I think also we're going to need to figure out how to schedule memory resources. And then leverage a composable memory, which is a virtualized memory pool that makes it easier to move memory around between compute nodes as well as within a GPU itself. And then we have to figure out how to migrate things, right? So a lot of times classic memory, at some point you have to start garbage collecting, defragmenting things, or compacting, bin packing things. Same exercise. So it's interesting. The industry kind of goes in a spiral. All these concepts have existed for decades, but now we got to figure out how to apply them to this new set of circumstances. Yeah, but some of those basic principles are still going to need to be applied in this area.
I'm not sure I fully understood when you said the composable memory there and the virtual memory, sharing it around.
Yeah,
I think I get it, but not fully.
It's I kind of jumped ahead. I didn't explain that concept. So up until now, DRAM has been, I call it chained to the processor. It's either chained to the GPU as HBM memory, or it's chained to a CPU, and it's the system memory on the DDR bus. And so what's going on in this memory revolution is it's not quite as visible as the accelerator revolution, but there's definitely a memory revolution underway. There's a big effort to put memory on its own fabric. So one of the first steps toward that was the CXL consortium, which was formed in 2019. And that was the realization that we can't use these classic parallel bus architectures and scale memory much more. We're out of gas on. As a matter of fact, if you look at a high level, the ratio of memory to compute cores has been deteriorating for years and years. And now we've got to totally reverse that. So the only way they could do that was to actually start using more of a serial bus architecture. And the first one to come along is PCIe. So the CXL consortium now allows you to take memory modules and plug them into a PCIe bus and extend the memory over the PCIe bus. And this is standard DDR DRAM memory. So it's high. It's reasonably high speed memory, and allow you to expand within a compute node. And then across compute nodes, you may know already that a lot of people have built PCIe switches. So now there's what they call CXL-enabled PCI switches coming out. CXL, by the way, stands for Computer Express Link. It's just the acronym for this whole idea of creating additional pools of memory that are external to the system buses, but allow you to pool and share memory. So sharing memory is really kind of the ultimate, because I think there's use cases in AI where people want to save like the entire chat history and then be able to put that back into a prompt quickly, or some pieces of it, and have more accurate answers or relevant answers and things like that. Well, you can imagine at some point in the not too distant future, we're going to have the ability to put an entire group. Let's say they're all interested. This group is all interested in travel to Hawaii, or wherever. We can put all their chat history in one pool and share the responses and questions among an entire pool across multiple nodes. Yeah. So collaboration is now going to be enabled. There's already people we can collaborate to a certain degree, but I think we'll be able to take it to a new level and to a new depth of history. So that's also exciting. This ability to use a memory pool. The memory pool becomes basically a first-class citizen over time in a data center, and becomes a repository of all this chat history.
If I'm understanding that correctly, it's like bringing Google Docs to your chat history. And now I can comment on some of your chat history, or I can just jump in and say, hey, now explain more this, whatever you said from your answer, but now I get to take the wheel and drive.
Yeah, it's kind of like, it's like car applications, right? It's a crowdsourcing kind of thing. You look at the traffic, you have all these data points reporting on the traffic everywhere, real time. So here you can crowdsource the responses in one sense and get, I think, higher quality responses, or more closer to real time responses based on changing conditions or whatever to what's going on. And so we started prototyping this. So if I put a link in our to a blog that we have on how we took Llama Index and this very simple RAG LLM pipeline and started creating that shared repository. But we're still working on it. That's more of a toy demo, to be honest with you, at this point. But it does show that we can make some of those pipelines what I would call better, cheaper, and faster. Better in the sense that we're going to get a higher quality response from aggregating all this chat history. Cheaper because we actually have, because of the additional bandwidth of adding this CXL memory to these compute nodes, we get more bandwidth, higher queries per second, which, per node. So that drives down the cost per query. And then faster because we're recalling everything from memory. So when you look at some of these workloads which require rapid lookup of all these different memory objects, it's hard to beat, a random direct seek off of a memory device as opposed to going into a storage device and loading a whole block at a time and trying to parse through that.
So really, it comes back to what you were saying earlier on this elasticity and being able to have the elasticity of memory along with the elasticity of everything else. Memory in both ways, on the training side of things, but also on this inference side of things.
Yep. The whole pipeline, even the pre-training, the ingest area, you have the emergence now. I just got back from the Ray Summit. There's emergence of these multimodal heterogeneous workflows, right? Multimodal meaning, okay, it's coming in as voice. This guy is speaking Korean, and now we got to turn it into vectors and embed it, and then we got to run it through a translator and have it within milliseconds come back and speak in English, like a universal translator. So, so that kind of modality switch, makes the models a lot harder, especially when you get to video. The video images are much bigger than text prompts, and so I think for those we'll need to increase the token generation rate by at least 5x, equivalent of 5x just to handle those kinds of things, which means more.
Is it different though?
Yeah.
When you're looking at the training side of this elasticity of memory versus the inference side and how you set it up and how you think about it?
Yeah, no, there's definitely differences, but I think the other interesting thing about our industry is originally they were very distinct. As a matter of fact, you could just train on GPUs and you could even use CPUs to do the inferencing, and you only needed one or two of those to do it. But now I think there's convergence. I mean, there's inferencing going on in the training phase. That's how some of these reasoning models got developed, and then there's training going on in the inferencing phase, the other way around. This fine tuning, and this need to have a LoRa adapter per person, right? So you'll have your own LoRa adapter. I'll have my own LoRa adapter. And as soon as this general purpose model finds out, oh, it's you, it'll drop in your LoRa adapter and now it has customized responses for your your preferences or whatever, right? So I think it's going to get moshed together more distinct.
Yeah.
And so we need a really elastic, flexible and scalable memory architecture. And I think this memory architecture needs to go up and out. So it needs to be a scale up and also a scale out. Just scale up just because going back to first principles in physics, I mean, a nanosecond is a nanosecond, right?
Yeah.
And so if you want to really compress latency of these more complex workflows, there's going to have to be some level of scaling up. On the other hand, if you want to handle the entire, planet's AI needs, you're going to need a scale out. So it's going to be interesting. And there are not only new memory technologies that are disaggregated like CXL coming out, but there are also new fabrics that are coming out that also will support this scale up and scale out. So your audience should read up on, there's an emerging standard called the Ultra Ethernet Consortium, which will address some of the scale out issues. And then there's another consortium called the Unified Accelerator Link, which will address memory scale up. So those are emerging standards along with the CXL standard I just mentioned that I think are all going to, over the next couple of years, make significant differences in this memory bandwidth capacity latency problem.
Well, I remember I did a breakdown on a few of the Facebook engineering blogs or meta engineering blogs, and they were talking about their GPUs and how they train Llama and all that fun stuff. And one thing that they mentioned was, I think it was 25,000 H100s or A100s. I can't remember exactly which. 24, they split it up. So I'm pretty sure they had 48,000 in total, but they said, we don't know what's going to be better. We want to test which one is better. And one of the tests that they did was with that Ultra Ethernet to see if it was faster versus now I'll have to check again what the other option was that they had.
Yeah, well, the people are using InfiniBand as one choice.
The InfiniBand, that was it. The classic InfiniBand.
Yeah. And then there's standards. Well, part of it is there are no standards. So I believe what Meta has done so far is sort of a proprietary way of doing what they call packet sprayings across Ethernet, which is one of the things that the Ultra Ethernet Consortium wants to standardize on. Yeah. So a lot of these networks, I think and I'm kind of drifting off of memory into networks, but I'll go a little further. A lot of those networks, I think, were designed primarily for more like north-south traffic than east-west traffic that you see in these clusters that need to exchange at high speeds all the weights and values and all that kind of stuff. So that's really the ultimate problem they're trying to solve. Yeah, and it has to be reliable. Can't drop packets and retransmit. It takes too long.
So one thing that I did want to touch on was how this all affects operations, right? And the scheduling workflows and the pipelines around that, the compute instances, the composability of the GPUs, and schedulings that now need to take into consideration the GPU status. You had mentioned how it's not just scheduling for the GPU status, but then the memory scheduling and all of that. And so you're really dissecting the scheduling workflows in ways that it feels like we're not necessarily thinking about it today, but it probably would help us to think about it.
There's multiple dimensions to the scheduling problem. one quite honestly is, it's more of an organizational thing, right? How a company is organized, or an enterprise or a cloud service is organized, and so it's basically an allocation of a scarce resource at the end of the day. It's an economic problem, right? So there's that dimension. Okay, who has priority? How do we assign priorities to jobs? Some jobs are batch jobs. I mean, it kind of at a trivial level, you can say, well, this is a batch job. It can be bumped off. This one's an interactive web session. It has to meet a certain kind of SLA. So you're going to have in a different infrastructure, and they probably, most likely, I would imagine, get partitioned. This area maybe just for more batchy kind of things, and this area is more services kinds of things, or ongoing streaming things. So that's one level of cut at this problem. And the other level of cut is that, okay, how do I balance among multiple different criteria how resources should be allocated? So, for example, do I care more about utilization of memory and utilization of GPU? Is that the primary dimension of scheduling, or is the primary dimension of scheduling the SLA? What is the end throughput of a single session? What is the overall total throughput? And what's the long tail latency of any individual? Maybe the most important criteria is actually making sure that the P99 of a session is no more than X. Otherwise, I'm going to have a customer churn and dropout. So all those things have to be figured out, and then mapped to some sort of what I think will need to be a highly elastic infrastructure. A lot of people are building their infrastructure on Kubernetes, which is great, but it doesn't go nearly far enough in trying to address these new problems. I mean, it's designed to do a horizontal scaling and vertical auto scaling. It has a lot of neat infrastructure, but now that the accelerator, was designed for these CPU architecture, now the accelerator is becoming more important, and the memory is becoming more important. So it's funny that the components of not necessarily the actual node itself is becoming the main, these individual components is becoming more important to schedule more directly, is what's happening now.
And do you see a open source project that is built on top of Kubernetes coming through and helping that? Or is it something that just Kubernetes itself, the way it was thought through and the primitives there, are not going to be able to do the trick?
I think, no, I actually, there's there must be at least a half a dozen scheduling projects going on, that are Kubernetes related. And some of them are also, trying to address various aspects. And it right now is still very much a fluid thing. It's not clear because the reason things are not clear is because things are changing so rapidly, even at the top level of the stack. Just basically the way we put together and deliver models. I would say last year was the year of model proving, right? Which model is the right model? Is it going to be an open source model? Is it going to be are we going to use APIs in the cloud, and those are the only good models? And I think that pretty much the people now have kind of decided, okay, most of these models, open source models, are good enough. At least good enough for large language models. They may not be good enough for other kinds of multimodal models yet, but definitely that area is out of the way. And so this year, I think, was more about RAG, right? How do we start delivering putting these things into products and services, these AI things? And toward the tail end of this year, it's been more about multi-agentic RAG, and now the training area is going through another iteration. Now people want to start having these things reason more, So there's so much flux, is what I'm trying to say. There's so much flux at that level that whatever schedule you build is going to have to be very composable itself, and also probably able to teach itself over time. Have some sort of AI ops element to it, because it's complicated.
So that's fascinating to think about. The flexibility needs to almost be the number one design principle.
Yeah, I think architecturally it needs to be flexible, almost to an extreme. And then, like I said, there's these new trends right now. A lot of schedulers don't even consider memory, right? It's just, it's just like they didn't consider what GPUs when they originally built the original schedulers for Kubernetes. Now we got to start spending more time more of the action is there, even though they're still tethered to a CPU. You talk to a CPU as a Kubernetes node, but you're really driving the GPUs that node contains, and those GPUs have their own network too, by the way, right? So they have their own NV mesh and things like that. So yeah, it's just this is really a time of a lot of experimentation, I would say, but it is still evolving very quickly, and there's probably going to be multiple right answers. is how I see it. I mean, that's how I see the like I said, I think there's at least a half a dozen scheduling projects. I mean, there's Q and there's Unicorn, and I just heard another one from Alibaba, I think, is working on one. So there's several, and these are open source scheduling projects.
Yeah, I guess my biggest question is how much of that is a square peg trying to fit into a round hole?
Yeah, I think I think some of these projects have been driven by, particular, hyperscalers and their or large scale deployments and their kind of unique set of circumstances. So that's why there's so many of these things. It's going to be driven by, like I said, at least by organizational considerations and economic considerations, and also driven by, their technology stack that they chose, and for that generation of deployment. Yeah. So, it's challenging, but I think my expectation is that some of this dust will start settling in the next couple of years, and we'll see more distinct patterns emerge. And my hope is that by that time, you'll see memory get more respect in the industry, or awareness and use as part of solving some of these AI problems, which again, people have this high level perception of their GPU bound, but I think really when I listen to a lot of these talks, at the end of the day, they're really memory bound problems.
And that's why I feel like it is you going back to first principles, because you're saying, the GPU is there, you are bound by the GPU, but what do you want from that GPU? Where's the real bottleneck? If it's at the memory layer, then we might want to start there.
No, exactly. I think I like to say that in a Western cultures, people say, when you look at a problem, here's point A and here's point B, and you draw a line between A and B, and that's the direction you go to solve it, or the direction. And maybe in Asian cultures, it's more of a spiral. Everything is a yin and yang, it's a circle. But I think reality in this industry is a combination of both. It's both a vector and also a spiral. So you have this
spiraling around.
Yeah. So you have this rotation. So right now we're in a rotation where, it's the perception at least has been we have a huge GPU shortage or whatever. But I think. And at some points, it's been the industry's been network bound or storage bound, but I think memory bound is the next thing coming, or it's already here, as people just don't acknowledge it, and they're trying to, like I said, do as much ledger domain as they can I call it ledger domain with algorithms to spread out the memory problem, distribute it as much as possible, or quantize it. Right? It's okay. We're not going to use such accurate, FP16 down to int4 or whatever we're trying to do to shrink the size of these things. But nonetheless, a lot of the fundamental equations say, hey, you want these bigger prompts and models or more sophisticated things. Your KVs are gonna, your weights are gonna go up quadratically, right? Yeah. So even if it's quadratic with 4 bits, it's still quadratic versus quadratic with 60 bits. It's just mushrooming. So I think there's like I said, I think it'll be memory's turn to be in the docket and then in the limelight in the next 12, 18 months to solve some of these problems.
Do you see it also coming to the consumer hardware that we've got, and this amplification of memory on my laptop or on my cell phone?
Well, right now it is kind of a cram down situation. So yeah, you have extra considerations in like a handheld mobile device. How the power budget and things like that. So actually, I remember listening to a talk the other day from Qualcomm. It was amazing how much they're able to start putting some of these, visualization AI kinds of tools. They're starting to put those even on a phone, but they're going to need to carve out 8 gigs, 10, 16 gigs, 32 gigs. And so there's some limit to that, how much you can quantize things. But so I think to that point, I think, yeah, they're squeezing out, every last drop of blood we can out of algorithms and quantization. And at some point, you're going to we're out of algorithmic tricks. We've got to do something. And I think on the edge, you can get away with that. You got a smaller screen and all that kind of stuff. You don't have to worry about the resolution and certain other factors like that. But yeah, I think for a lot of other use cases, we just gotta, refactor the memory stack as well as the GPU stack and everything else. Yeah.
You're telling me there's not enough fancy math in the world to squeeze a little bit more out of that algorithm.
Yeah. Well, I mean,
we got to go somewhere else.
I mean, that's what happened in general with AI. I mean, AI has been around for years, decades. And the problem was they didn't have enough compute power. And so finally the economics and the ability to connect these things in some reasonable network like InfiniBand made it viable to run these kinds of basically grinding problems. And so, yeah. So that was a limiter. And I think, like I said, to take AI to the next level, which I think is going to be very exciting, this multimodal real-time stuff, the ability to implement robotics or whatever, that's going to require, more than just the algorithms to solve it. I mean, we're going to need algorithms. I don't want to belittle what those people are doing. They're doing some incredible work. But
no.
But everything falls back. I think the rubber hits the road kind of in the operations area. It's nice to do all this R&D, but we've got to put it in production. We got to make it economical, and we got to make it secure and meet SLAs, all that kind of stuff. So I'm kind of interested in that, applying that, all this innovation and making this stuff really tangible for everybody to use.
And speaking of making it more economical, does the excess of memory, do you feel like there will be new strategies that will help make it more economical, like we were talking about with the checkpoints and how you can kind of slowly roll the checkpoints from one stage to another via the memory path? Or because when I think of gigantic pools of memory, I don't think cheap.
Yeah,
right?
No, they're
those things
expensive.
don't necessarily
Bingo.
go in my head.
Yeah. No, actually, years ago when MemVerge got started, the inspiration back then was going to be the availability of cheap memory. So several years ago, Intel introduced something called Optane, or persistent memory, and its cost per bit, its read access time was the same as DRAM. Matter of fact, you plugged it in the same DDR slots as regular DRAM, but its cost per bit was like 1/4 of DRAM. So you could actually build a much larger memory pool and drive down the cost per bit. But so that's one aspect. Unfortunately, they discontinued. That was a proprietary architecture. They discontinued that. But within the memory hardware industry, there are new kinds of memory technologies emerging. Also, there are also kind of converged memory architectures emerging. So SSD is much cheaper than on a cost per bit than DRAM. So people are trying to build these kind of hybridized memory / SSD. Matter of fact, they're referred to as memory semantic SSDs.
Nice.
Because the problem with the SSD is that the cost per bit is slower, but the access time, lookup time is a lot longer. So maybe instead of 100 nanoseconds, now you're at 10 microseconds. It's like a couple orders of magnitude higher. So part of the solution is to try to use a combination of those in a very clever caching way. And some of these, some algorithms, not all of them, are more predictable from an application standpoint. So you have a better chance of using that kind of caching algorithm. Others are going to be totally random, just because, if you're serving inferencing out there, who knows who's going to come up to the chat and ask some off the wall question next. You never know. You have no idea of what kind of access you might need. So I think. And then there are fundamentally new memory technologies. So I know some of the largest firms, VC firms are looking at funding some of these new generation memory technologies that will kind of bridge that substantial gap. There's like a couple orders of magnitude difference in performance, but also in cost per bit between DRAM and SSD. Yeah, I think that'll also have to happen as well over time.
Now, the other piece that I wanted to dive into was around what you had said before with these basically pools of memory that you can use in an elastic way. And so that you can avoid what I am sure everyone that is listening has had happen to them at one point or another in their life with those ohm errors.
Yep. Yeah, those are really annoying. That was the most annoying thing I learned about Kubernetes. Is like, good thing is it's a very elastic infrastructure for microservices and all that. Bad news is if you have if you're semi-stateful, you got a lot of memory you're dragging around and you get killed. It's not a pleasant situation. Yeah. And so
exactly.
So I think, it's interesting how Kubernetes is evolved because it was supposed to be a totally, stateless microservices. In other words, all these database and storage problems, okay, not in my backyard, put them outside the Kubernetes and connect to them. But I think that's not so easy to do, in my opinion, with some of these AI ML workflows. And so over the years, obviously, the Kubernetes community has done a great job of accommodating stateful applications and replica sets and all this other kind of stuff, right? You see it in more general purpose enterprise environments. And so I think this elastic pool, we're hoping to show this kind of demonstration probably in the not too distant future, where as soon as we detect memory pressure, like this, things are starting to either, because I think you can adjust. There is a project going on with Kubernetes where you can spill to disk or do disk swapping, which is heretical to original Kubernetes, philosophy, but they're allowing it now. But so we can either detect those kinds of swaps or detect when just before a node gets shot, preemptively shot for out of memory where a pod gets killed because it's about to run out of memory in the node. We can intervene in those and inject memory, or we can cycle the memory. So there's certain things, applications where the memory is actually sinusoidal or whatever in its consumption, and we can adopt, we can what we call wave ride the amount of memory based on where the application is running. Yeah, so those are things we're hoping to add to Kubernetes very shortly.
How do you even go about that? That's what I'm fascinated by is, you saw the problem. You said, all right, nobody likes these ohm errors. And we think that we can fix it these different ways by injecting memory or trying to swap it out. What are you thinking about when you're attacking that problem?
Well, the first area, it's from where I sit, we're kind of a piece of middleware. So first thing is we've got to get our hardware partners ready. So we are working with several players that are building memory pools. And so we've got to get that piece of infrastructure ready. And then the second piece is then we need to integrate with the Kubernetes layer. I think there's some relatively easy ways to integrate with the Kubernetes layer or create a hook or an operator or whatever. But longer run, we and I say we, the industry and a community are going to need to create some probably new standards, right? So, for example, in Kubernetes, there's something called I think it's a CSI. It's a standard for the storage layer, right? And there has to be an equivalent standard for how do we bring memory as a separate first-class citizen into a Kubernetes environment. Right now, we kind of hack our way in and show something, but with the existing schedulers and things like that. But I think over time we'll need to work with areas. For example, there's another initiative called DRA, Dynamic Resource Allocation, because right now everything is statically done. Once that node is set up by the kubelet or whatever, it's static. But what if the thing changes, right? So what if the memory increases and decreases? Or what if the number of GPU available or increases or decreases? that kind of dynamicism, I think, is just a general thing that the Kubernetes industry is trying to face up to. How do we make this even more elastic than it currently is? Right now, it's elastic at the node level, but even below that, there's some of these other elements that have, their own composability to them that need to be more dynamic. Yeah.
And do you feel so? I also like that you're looking at the node and you're saying inside of the node there needs to be a way to be more flexible and more elastic, and then the whole cluster and like you mentioned, up and down the stack, but also left and right in the stack. We need to rethink and look at all these different areas if we're coming into a world where AI plays such a big part of that. I wonder, is this only going to be the evolution for the use cases that we are trying to create AI products with? Or do you just see it that it's going to be better for the industry in general if we amplify on every vector that we can?
Yeah, well, with respect to things like memory, I mean, there's just tons of applications today that are getting killed and evicted or whatever, and so all those will benefit from this. So yeah, there's definitely that kind of benefit. Yeah, and I think same on the HPC side, those guys, that whole area, there's a lot of convergence between what goes on in the HPC world and AI. I think that area can also benefit from all the memory advances, general enterprise applications, databases. I think it'll be a broad-based thing, but right now, the way the AI movement is, quite honestly, sucking all the oxygen out of every other initiative right now. And it's probably the correct thing to do anyhow from a society standpoint. This is the hottest area. So, but once it settles down, I think some of these other innovations will obviously benefit the rest of the infrastructure, the rest of the applications that are still out there. They're not going to go away. Databases or anything like that, as an example. Matter of fact, they'll be part of this overall infrastructure, right? They're going to be our source of truth, our ability to avoid hallucinations, whatever, So they'll benefit from all these memory advances as well.
Bernie, incredible talking to you. And I want to just mention that I looked up the Meta blog post, and what I was looking at, they'd had the 16,000 GPU cluster, and it had remote direct memory access over convergent Ethernet,
right?
RoCE. That probably sounds familiar to you.
Oh, yeah.
I remember when I read that, I said, this could be in Greek, this could be in Chinese. I have no idea what that means.
Yeah, RDMA is called RDMA and it's RoCE, remote over Ethernet. RoCE is the acronym. Yeah, remote over converged Ethernet. So that's been actually around for quite a while, and that's the kind of the bread and butter of the current NVIDIA architecture. But like I said, I think people are ready to figure out how to take this to the next level and standardize things with Ultra Ethernet.
So I thought they had used the Ultra Ethernet, but it looks like they didn't, and they were using the InfiniBand for the other 16,000 cluster. And let me see. Hold on a sec. The RoCE was used for training the largest cluster. Despite underlying network differences between these clusters, they both provided equivalent performances. So what I remember from this is they said that the RoCE, or RoCE, as you mentioned, cluster, they were able to optimize it for quick build time, and the InfiniBand cluster, they had full bisection bandwidth.
Yeah, those two technologies they're all based on the same physics. Here's this network, and whether you're running, it used to be there was quite a technology gap between InfiniBand and Ethernet, but now that gap is pretty much down to the physical gap that from a physical PHY layer is basically equivalent, and it's really the protocol layer that's where the differences are. Yeah. So InfiniBand is designed to be a lossless configuration architecture, and Ethernet was always designed to be lossy, and there was trade-offs for that, right? And now, now they're all getting kind of mushed, or the Ethernet's going to try to absorb that type of protocol and compete with InfiniBand, quite honestly. So.